I'm Randy Anderson on behalf of our leadership team here. I'd like to welcome you to our November meeting of Science, Scripture, and Reason. And we are really delighted to have Dr. Kevin Birdwell back with us this evening. I think Kevin was here maybe 2 or 3 years ago. I can't remember exactly now. Just to refresh us, he is a research atmospheric scientist who currently works on the meteorological aspects of wind energy, weather model accuracy, complex terrain pollutant modeling, and nuclear energy safety. He has done work on complex terrain, airflow, meteorological operations, paleoclimate, and continues to do work related to environmental change. Dr. Birdwell has held a long-term interest in quaternary paleoclimate, which I had to look that up, but that's about 2.5 million years ago to the present time, during which time there have been glacial and interglacial cycles. And the understanding of how climate has changed in the past helps us to understand future climate change. Kevin holds a PhD in physical geography from the University of Tennessee, Knoxville, with an emphasis in environmental change. He also has been active in operational and research meteorology in various government laboratories since the late 1980s, and has been an adjunct professor of Earth's space science and meteorology at Lee University in Tennessee since 2014. Dr. Birdwell has also been part of the RTB scholar community since 2012. So Kevin, thank you very much for coming, and I'll turn it over to you. He's going to speak tonight on nuclear energy and sustainable climate. And he's going to teach us some things about the options of thorium and molten salt reactors. So thank you, Kevin.
Oh, thank you for that introduction. Can you guys see the screen there?
Yeah.
Okay. I may try to go a little faster at the beginning and then slow down a bit toward the end, because that's where most of the discussion of thorium is. I need to kind of give you a little bit of introduction to this topic, especially nuclear energy. Especially, I don't know how many nuclear scientists we may have in the audience, but most of the time it's good to talk a little bit about how nuclear power works. As I'm sure a few of you are aware, I have done a lot of speaking on climate change and meteorology, and that invariably leads to discussions of energy and how do we address that. And so that's really how I got into the nuclear energy issue. For the last 3 years, I have been doing work directly related to nuclear energy safety and, basically modeling the effects of accidents on power plants and things like that. And that ties into the meteorology. But in terms of climate change, so these are just some statistics. The world is producing somewhere around 37 gigatons of CO2 per year. And of course, if we were having a different discussion, I would point out that although we often have this discussion in terms of CO2, it's really about a lot of other factors as well, some which are man-made and some which are not. And we expect that to continue to grow by about 10% to the early 2030s. But then we have these climate goals that are saying that we need to reduce our emissions to 0.2 gigatons per year by 2050. And you see that that's quite a challenge from where we are now. And in 2023, about 13 trillion US dollars, or about 13% of the global GDP, goes toward fuel costs. And the global economy uses 637, is estimated that it will use 637 quads of energy by 2030. And for reference, 1 quadrillion BTUs is what we're talking about here. We're about 293,000 megawatts. Now we're at a number of around 570 right now. So what we're basically saying is we're expecting a 10% increase in global energy demand just in the 2020s.
Yeah, but may I interrupt you for just a minute?
Sure.
We're not seeing the full shared screen. Are you able to share your screen?
No, we're seeing the next slide.
We're seeing the next slides.
Yeah, okay. Let me try sharing again here. Okay, I think if I share this screen, that will probably do it in a moment here. Does that look better?
Yes, yeah, that looks great. Thank you.
Okay, great. And we're using about 103 million barrels of oil per day, and we should have about a 9% increase of that by the end of this decade. So about 80% of our energy comes from fossil fuels of some sort or another. And as you can see here from this 2022 chart, only about 8% of the world's power is actually coming from nuclear. Some places are a lot more than that. For example, in France, it's like 64%. And even where I live here in Tennessee, it's about 43% from nuclear. And I won't belabor this too much, but one thing that I really want to point out is this chart here. A lot of times when we talk about energy, we don't talk about energy return on investment. What is energy return on investment? It's basically how much energy do you have to put into something before, in order to get energy out, and do you get more energy out than you put in? And so you see from this chart here, ethanol is really one of the worst sources of energy because you can use 80 to 150% of what you get out to produce it. So in some cases, you're actually using more energy than you're getting out of it. And solar, next up the chart there, is sometimes good and sometimes not. It really depends where you are. So if you're at a northerly latitude, you're probably not going to do that well with solar, such as in Germany, for example. But if you're in the Sahara, you may do a lot better. Or if you're in, let's say, Arizona, wind energy does better in some places, but again, there are places where it doesn't do well. So, for example, where I work in Oak Ridge, Tennessee, is one of the least windiest places in the country, and we do have some wind turbines on a few of the local mountains, but I really wonder how much. In fact, actually, I was working at a NOAA lab at the time when they first started planning to put those up there, and we basically told them that there wasn't all that much wind up there. So I'm not sure why they decided to go ahead with it, but they did. And there's especially with things like wind and solar, because they're intermittent power sources, it makes a big difference whether this power source is buffered or not. So can you store the energy? So you can see the unbuffered is the yellow, and you do pretty well when it's unbuffered, but when it's buffered, your results are kind of mixed. And next up the chart there is clean coal gas technology, and then regular coal burning. Those have an energy return on investment in the vicinity of 30 to 1. So you get a lot of energy back for what you put into it, which is one of the reasons fossil fuels are so popular. Hydropower is very good. You're looking at 35 to 50 to 1. But there's only so much hydropower to go around, and we can't really power the entire world on the hydropower. Nuclear is an impressive 75 to 1. And that it doesn't make much difference if it's buffered or unbuffered because it's basically always available, depending on the type of nuclear power plant you use. And so that red line there is basically your economic threshold. So if your power source is left of that economic threshold, then you're really spending more energy to make it than you're getting out of it. And this reminds me of the parable of the minas in Luke 19, because everybody started off with one mina, and when the master came back looking for results, one servant had 10 minas, one had 5, and one still had 1. Well, in terms of energy, for me, doing the ethanol is kind of like just coming back with the 1 mina, and doing the nuclear is coming back with the 10. So I think in terms of a Christian perspective, we need to be looking at what energy sources are really going to meet our needs, not only our present needs, but needs in the future. I mean, the world is looking at possibly having energy demand as much as 50% more by 2050 than it is today. And so if you're trying to decarbonize or move away from fossil fuels, that makes the issue even more difficult. So to achieve excuse me, CO2 stabilization at low levels, energy would need to come from many more carbon-free sources. And currently, these are only about 11% of the global energy demand, which basically means that wholesale dependency on intermittent low EROI renewables could hinder decarbonization of the economy, because these sources at present serve as poor sources of base load power. And I'll explain that in a moment. This is one of the reasons that coal and natural gas have been used so prevalently, because you can just have them laying around basically, and or stored in a tank, and when you need them, you burn them. Whereas with wind and solar, while they definitely have their place, I'm not trying to say we shouldn't use wind and solar, but they are intermittent. They're not always available, and storage technology is still not that far along. So it presents a real problem especially for times of day when energy demand is the greatest, that doesn't necessarily line up with peak solar and winds. For example, in the case of solar, you don't get much solar in the early evening, but yet that's when you often have peak demand and power. And so what you really have to look at when you're talking about energy sources is these 6 factors here. Resilience. What are the environmental circumstances? What I'm saying here, does your energy source work in a wide range of environmental conditions? So for example, solar works in the day, but not at night. Wind depends on pressure systems that move around the globe. Is your energy source scalable? In other words, is it just something that's useful at a small scale, or is it abundant enough that you can scale it up to use for things like an entire society? Is it abundant? How much of the resource is available? So for example, if we wanted to use platinum, as platinum was involved in our energy production, then we might have a problem because we only have so much of it. This is actually one of the problems that we currently face with things. I think hydrogen would be a good example. You can make hydrogen and you can use it, but is it really abundant enough in the form you need to use it on a wide scale? I would say right now the answer to that is no. Also, is it affordable? Is it going to be economical for a significant portion of the population? And is it reliable? Is the energy source dependable in widely varying societal or environmental circumstances? And lastly, is it flexible? Can you transport it somewhere? Is it where you need it? Or if it isn't, can you get it to where you need it? So this thing about base load. Base load is essentially the minimum power demand that you need at all times to meet customer requirements. And if any of you have been involved with the power utility industry, you know that power demand varies significantly, not only seasonally, but even daily and even through hours of the day. And the power company actually has to do a lot of manipulation of the power grid to make that all balance out. And baseload power is basically the minimum you need. If your power source is intermittent, then you have to be concerned about is it going to be available to meet that baseload power? Fossil fuels obviously are capable of doing that, and for the most part, nuclear is as well. Now, sometimes conventional nuclear doesn't respond as quickly. In other words, it takes time to ramp up the power level of a large power plant or tone it down. But more or less, it is a good baseload power source. And actually, as I get through to some of the later advanced nuclear that we want to talk about, this will become less of an issue. Molten salt reactors, which are the type of nuclear reactors I want to get to, they run on liquid fuel and instead of solid fuel. And because of that, the ability to ramp up power is much better. And a 24-hour supply of energy is indispensable to the safe and reliable operation of so many things in our society, things like utilities, heating and cooling systems, mass transit, medical care, manufacturing, even emergency services. Now, sometimes people are concerned about safety when it comes to nuclear power, and it might surprise some people to know that despite some rather famous accidents like Chernobyl and Fukushima, nuclear power is actually among the safest power source there is, right along with wind and solar, when you consider how much power you're getting per unit. And in this case, oil, coal, and most fossil fuels actually have a much worse safety record. I don't have time to present on it here, but I actually gave a presentation when I was at RTB a few months ago on nuclear accidents. And it's really unfortunate that Chernobyl, which was not designed like Western reactors. The Chernobyl accident was by far the worst nuclear power accident, period. But it could have never happened in the West because of the way it was designed and the way Western reactors are designed. But unfortunately, it still had a very negative impact on the construction of nuclear power plants for really a decade or two after the accident. So the next question is, how can nuclear move renewable energy production forward? And so I was just talking about the decline in reactor construction for a while. So there's you a chart. You can see that it really peaked in the 1960s and 70s, and it was already declining some. Chernobyl happened around 1986, but you notice the couple of decades after that, the number of reactors built remained quite low. And these are global numbers. And then you actually, if you look close, there's another minor peak around after 2011 when Fukushima happened, or minor decline rather. So really, nuclear power plants operate the same way that most other power plants operate, in the sense that they produce heat, and that heat is used to produce steam, which turns turbines and creates electricity that's sent out on the grid. This is true of a coal power plant, for example, as well. The difference is that in the case of nuclear, you're splitting uranium atoms and producing neutrons. And if you have enough uranium around, you continue to split more uranium atoms, and this process produces heat. And that heat is usually transferred by water to the steam generators that then transfer the steam to the turbines. Now, there's actually three types of fissionable fuel. Reactors today generally use uranium-235, but also it is possible to run a reactor on
Internet link.
it can be
Oh,
are you guys hearing me?
oh, there we go. We had about a 1 minute pause in the internet. So if you can back up mentally about 1 minute, that would be great.
U-235.
Q235.
Okay. Sorry about that. So U-235 is what basically is used in almost all reactors today. But it only makes up 0.7% of natural uranium. Most natural uranium that is mined, 99.3%, is uranium-238. Uranium-238 can be burned in certain reactors, but it is not that useful directly, and so it is not generally used. And if it is burned, it turns into plutonium-239 in many cases, which is not usually desired because that's typically used more for, nuclear weapons. There's also uranium-233. Uranium-233 does not exist in nature, but it can be made. And that comes into the discussion about thorium that we're going to get to shortly. All right, so there are also fertile atoms. So you can, fertile atom is something that isn't fissionable directly, but it can be turned into a fissionable atom by throwing neutrons at it and converting it to another element. And that is true uranium-238. As I said, you can end up with plutonium-239 from that with a few days of reactions with neutrons. And in the case of thorium-232, if you bombard it with neutrons, you end up with thorium-233, which rapidly decays into Pa-233 and then protactinium, and then to uranium-233. And that process takes roughly 4 weeks. So it's really, when you're talking about using thorium in a reactor, you're really talking about converting it to U-233. Now, in a standard reactor, most of the ones that we know about today, that we have today, this is just a basic diagram. And most reactors have all of the same features. You have a central reactor core where the fuel is bombarded with neutrons. You have a moderator. A moderator is something that reflects the neutrons back into the reactor so that you get more fissions and keep the process going. And in most cases today, water is used as the moderator, and it's also used as a coolant. And then you have that water sending heat to the steam generator, to the turbine, to the generator, to the electric grid. And of course, most people identify nuclear power plants with these big cooling towers, but really those are just the cooling towers. Those are just releasing heat and water vapor. That's not really where the nuclear reaction is going on. And so this is just an example of some nuclear fuel rods. As I said, fuel today is in solid form. And so it's processed into these uranium oxide rods that are usually coated with some other substance. Zirconium alloy typically. And there's several kinds of reactors in use today. Probably the most common one is the pressurized water reactor. Nuclear engineers use these acronyms for different kinds of reactors. So we call that a PWR. And then there's a boiling water reactor, which is similar, but runs at a little bit lower pressure. than the PWR, and that's called a BWR. And then especially after Chernobyl, the Russians developed a VVER, which stands for water energetic reactor. It's actually similar to Western reactors in most respects. There's the Canadian deuterium uranium reactor, which is called CANDU. And what's interesting about it is it uses heavy water as a moderator, and that allows them to burn natural uranium without having to enrich it slightly. They didn't have a way to enrich their uranium back in the World War II era, so they developed these reactors and made it a lot easier for them to get into the nuclear power industry. And then over the last decade or so, we're now developing molten salt reactors again. And I say again because I'll talk about the original one in a few moments. Typically, when you're burning nuclear fuel today, these solid fuel rods, they only last so long in the neutron bombarding environment in the reactor. And unfortunately, you typically don't burn up more than 5% of the fuel before you have to take the rod out of the reactor. And so this is why you end up with waste, because there's just a lot of in fact, we don't even use the term waste in the nuclear industry that much. It's really called spent fuel because, so-called nuclear waste really has a lot of useful energy in it. It's just that it's typically too expensive to recycle it with the type of reactors we have today. And also, your typical light water reactor, as they're typically called, must be shut down every 18 to 24 months to replace the fuel. That shutdown might last for a month. The exception for that is the CANDU reactor, which can be fueled online without shutting it down. So the fuel rods are typically uranium oxide pellets with a zircaloy alloy on top of them. And they're usually enriched except for the CANDU reactors, they're usually enriched about 3 to 5%. That means that they've taken that 0.7% U-235 that naturally occurs in mined uranium and raised that amount to about 3 to 5% of the total uranium. That allows you to get better reactivity in your reactor and keep the process going better. Now, I've sort of alluded to this already, but there are really two types of reactors when it comes to neutron bombardment. Most reactors use what's called the thermal spectrum. It would take a little time to talk about this on its own, but basically, it's easier for the neutron to hit another uranium atom in the thermal spectrum. And so most reactors are in that zone. And if you're talking about thorium and converting it to uranium-233 and then burning that in a reactor, you want to use the thermal spectrum. There are some reactors that are called fast reactors that use faster neutrons. So what we're talking about here is how much you slow down your neutrons when they are released from a splitting atom of uranium. So that's what your moderator is doing. So in the case of a thermal reactor, you're using water or graphite or something like that to slow down the neutrons so that they have a better chance of hitting other uranium atoms. In the fast reactor, you're producing more neutrons, so you're not so worried about slowing them down because you've got enough of a supply of neutrons that you can still hit enough of the other uranium atoms. So there's a picture of some graphite there. So today, most nuclear reactors use heavy water as a moderator and a coolant. Sometimes you use a gas like helium. Those are less common today. Or you might use something like liquid metal. So TerraPower, which I'll mention in a minute, is developing something based on sodium. but the coolant affects the reactor's efficiency and safety. So one of the problems with using water is you're running your reactor at something like 300 degrees Celsius. And obviously, water is not going to remain a liquid at that temperature under standard atmospheric pressure. So you have to pressurize it. And so in today's nuclear reactors, you're typically running your water pressure at 150 atmospheres. And if you're in a boiling water reactor, it might be a little lower, but it's still 90 atmospheres. So, there's no danger of a nuclear explosion with a nuclear reactor because the reactor, the nuclear fuel would have to be far, far enriched, more than it is in a reactor. What your danger is having a leak in that pressurized water, which then leaks radioactive materials, fission products with it. That's the real concern there. But if you had a coolant that didn't have to be pressurized, you wouldn't have that problem. Now, in the past, some reactors have used graphite as a moderator instead of water. So there, in that case, you're using a solid to reflect the neutrons back. But there you also have to be careful because if you design your reactor, in the case of Chernobyl, for example, they didn't have one pressure vessel. They were trying to save money, basically, and not pressure vessels are very expensive to build. So they didn't have a pressure vessel in a Chernobyl reactor. That was what's called an RBMK reactor. And they had all these small pressure tubes surrounded by graphite. But the problem was the way they were designed, that if your water started to boil, your graphite would actually reflect so many neutrons that the reactor would actually start to speed up. And that's actually what happened when the Chernobyl accident occurred. So in today's nuclear reactors, you have the advantage of a highly concentrated energy source, a good overall safety record, but there are several disadvantages. In the West, we have a lot of regulation on nuclear power. You have expensive and slow construction. You have extensive containment. So like a typical containment building for a Western reactor has like 3 feet thick of reinforced concrete, and usually maybe say a 5/8 thick, inch thick stainless steel container inside of the concrete. You have limited total energy extraction. You're not using 95% of the fuel. And then there's a question of how much U-235 is there available. It's only a small part of the natural uranium. There's plenty of it available today, but eventually we may not have as much. And then you have the fission products, because you don't burn up that much of the fuel rod before you take it out. You end up with a lot of fission products, or what is often called waste. And what is waste? Well, it contains uranium-235 that's not been burned. It contains lots of 238, a little bit of plutonium that's been converted from the 238. It contains cesium, strontium, iodine, many other fission products, actinides like neptunium, americium, curium. These all add radioactivity. And, many of these products have to be stored for tens of thousands of years. Now, there is a good side to this, and that is, people have this idea that there's nuclear waste everywhere, but actually, if you took all of the US's nuclear waste and put it in one place, it would probably occupy a football field about 30 feet high. So it's really doesn't take up that large of a space. But now what I want to get into is what we're really here to talk about, and that is how can we do this differently? How can we do this better? And I'm just going to read this because I think it's a great statement. Now, if you don't know who Alvin Weinberg was an incredibly smart guy. He was the director of Oak Ridge National Lab from 1955 to 1972. He became the director at age 35. and I can tell you from someone who works in the Oak Ridge area, that's just unheard of. He essentially was Mr. Nuclear Power. He played a large part in inventing nuclear energy for power use. But he says here about molten salt technology, and that it's entirely different from the technology of any other reactor. To the inexperienced, fluoride technologies, which he's talking about molten salt there, is daunting. Perhaps the moral to be drawn is that a technology that differs too much from an existing technology has not one hurdle to overcome to demonstrate its feasibility, but another even greater one to convince influential individuals and organizations who are intellectually and emotionally attached to a different technology that they should adopt the new path. It was a successful technology that was dropped because it was too different from the main lines of reactor development. And I hope that in a second nuclear era, that fluoride reactor technology will be resurrected. So in the 1960s, or really in the 50s, Oak Ridge National Lab and Alvin Weinberg began experimenting with molten salt and with the idea of having a liquid fuel and having the fuel in the molten salt. So therefore it could move around. It wasn't just stuck in one place. And this kind of started from what's called the aircraft reactor experiment in the 50s. So believe it or not, the Air Force wanted to be like the Navy. The Navy had all these nuclear powered ships and submarines, and they wanted nuclear powered aircraft. And in that day, it was of interest because they wanted long range bombers that didn't have to refuel. And so they asked Oak Ridge to experiment with this. And there actually was some work done on this. It was called the ARE experiment, aircraft reactor experiment. And they actually did create a reactor in an airplane. It was actually tested 215 hours of flight time over New Mexico and Texas between 1955 and 57. Now, Alvin Weinberg knew that this was not really the best idea, but he saw this as a means to an end. He realized that molten salt in a nuclear reactor could have some potential benefit, maybe not in an airplane, but maybe in other ways. Well, that led to the MSRE, the molten salt reactor experiment. So this is a picture of the inside of it. And the molten salt reactor experiment ran on what's called FLIBE. FLIBE is a molten salt that consists of fluoride, lithium, and beryllium. And that's where the name FLIBE comes from. And it burned both U-235 and U-233 that had been produced from thorium. And this reactor successfully ran for about 4 years. After that time, they basically lost their funding and were required to shut it down. Now, Alvin Weinberg campaigned vigorously. He basically told the federal government, this is the way you need to go with future nuclear power because it's just better in so many ways and safer. But at that time, the government was more interested in the existing nuclear fleet of light water reactors. They were interested in fast reactors. They were interested in plutonium. And if you research this topic a little bit, you find out that there was some politics involved. I think there was a desire to, frankly, to redirect some of the funding to some nuclear work in California at that time. So essentially, Alvin Weinberg was very disappointed, and it wasn't that long after that he resigned from Oak Ridge. But I really wish that had turned out differently because I think if he had been able to move forward, I think we probably would have had power plants based on this on this technology as probably as long ago as the 1990s. And I'll explain why I think the potential for a molten salt reactor is better in the long run. Now, they did not put a thorium blanket around this reactor. But they did produce uranium-233 from thorium from a reactor. But basically, in theory, what you could have done here is you could have put thorium around the reactor core so that when the neutrons came out of the reactor, they would hit the thorium. So while you're making power in the reactor, you're also converting the thorium into more fuel, into uranium-233. But this reactor ran very successfully and very smoothly for 4 years. So it really demonstrated the potential of this type of a nuclear reactor. And this is just a diagram of the molten salt reactor experiment. But I think the two notable things there that are different is number 10 and number 13 there. Number 13 is the freeze valve. So if something happened something happened to the reactor, then the molten salt with the fuel in it would go down into that tube that goes through the 13 label there. It would turn that frozen salt into liquid, and then it would all flow down into number 10 and 11 there, the fuel drain tanks, safely removing the fuel from the reactor. So, in recent times, we've had issues with a few reactors melting down, and that's essentially when, the coolant, the water, somehow got removed or boiled away, and then the reactor core gets too hot and melts down. With this molten salt technology, that's not a possibility, because you don't have to have somebody sitting there saying, oh, I have to turn on some emergency cooling system. It just drains down, melts the freeze plug, and drains into the tanks, and you just walk away. So that's one great advantage right there in terms of safety. So this is a picture here of a graphite reactor, original graphite reactor core in Oak Ridge that was being worked on back in probably the 1940s. Now, the molten salt reactor experiment basically ended in the early 70s in Oak Ridge. And in the early 2000s, somewhere in the 2000s, the data from it was released to the public domain. Well, somewhere around 2009, people from China toured Oak Ridge and got that public domain data. And they decided they were going to build one of these reactors of their own. And so with a few tweaks, but basically it's based on the Oak Ridge design. And they now have an operational molten salt reactor using FLIBE in northwestern China. And their goal, this is a prototype reactor, but their goal, it's a 2 megawatt test reactor. It's very small, but their goal is to build molten salt reactors, even using thorium by the 2030s. And I will say that the interest in this in the US basically came back around, I would say, around 2010, give or take a few years. There were a number of people that promoted it, people like Kirk Sorensen. And since that time, it's gained ground. So, for example, about 10 years ago, Oak Ridge National Lab started having a molten salt reactor conference. And that started off very small, but I actually just attended that conference about 2 weeks ago. And it's in its 10th year, and it now hosts about 400 people who are actively researching in this area. So it was actually very encouraging to see that many people working on this. So everything moves in steps. And in terms of using thorium, the CANDU reactors I mentioned earlier, they're now experimenting with using HALEU. HALEU stands for high assay low enriched uranium. So this is, instead of enriching uranium from just 3 to 5%, HALEU is enriched from 5 to 20%. So basically that gives you a better reactivity and better burn up. Now you're still not burning up that much of the fuel, but potentially you can use HALEU and even combined with thorium to give you a burn up as high as 5%. And for traditional reactors, that's actually pretty good. And this reduces your waste production a little bit as well. So that's one first step. Now I mentioned FLIBE as a molten salt. This is very important because the molten salt's what's carrying your fuel and moving it around and helping you to remove heat from the system. A great thing about molten salts is you can use them at essentially standard atmospheric pressures, which means there is no pressurized coolant involved, and you don't have any danger of an explosion like you do with, if your pressurized water gets out of its piping system, you have a steam explosion. And steam explosions expand like 1,600 times when the water converts to steam. That's why you have these really thick containment buildings today. If you don't have the possibility of a steam explosion, then you don't necessarily have to have such an expensive and thick containment building. So that is potentially reducing your cost. But molten salts basically become liquid around, depending on the type of salt, there are several types, around 450-ish C, and they don't boil till you get all the way up to, say, 1,500 C. So that's another great thing about a molten salt is you have a wide range of temperature that you can keep it liquid. So you don't have to worry as much about it freezing or boiling away like you do with water. And it has a density which is 8.5 times more than for water at room temperature. And it's a great solvent for nuclear fuel. And it's also chemically stable in a high neutron gamma radiation environment, such as what you'd have inside of a reactor. There's also FlyNac, which is also experimented with and used in reactors. It has similar freezing and boiling points. It has a slightly less desirable nuclear cross section. That's talking about the likelihood of a neutron hitting another uranium atom. But it's still desirable as an intermediate coolant in a molten salt reactor for heat transfer without the presence of fuel. And another good feature of it is, I mentioned FLIBE contains lithium and beryllium. When you're dealing with lithium and beryllium, you're dealing with some radioactivity. So it means that it's, can be less radioactive. But it's not as good for chemical processing. And you will need that to not only clean the salt, but to remove useful material from the salt. Because there are fission products that are actually marketable in a molten salt reactor. Now, I'm going to mention a couple of, so in the early 2010s, the DOE, the Department of Energy, decided that essentially private companies would build the reactors. So beginning in the 2010s, there were a number of companies that came up with reactor designs, and I'll share with you some information on some of those as we go through this. But one of the more prominent ones is Kairos Power, and they are actually developing a FLIBE molten salt reactor. Now, they're not yet using thorium, but they are using a better type of uranium fuel called TRISO. And TRISO is essentially a pellet or that contains a graphite pebble, and inside that pebble is the uranium fuel. And the great thing about TRISO is the way that it's coated is it can't melt down, and especially in a molten salt reactor. And this reactor does use graphite as the moderator to reflect neutrons. They are currently building one in Oak Ridge that's going to be about 15 megawatts, so fairly small, but it's a demonstration reactor, and it will be likely online as soon as sometime in 2026. So this is one of the really will be possibly the first molten salt reactor online in the United States since 1969 in the MSRE experiment. There is also a small one, a 1 megawatt research reactor that's supposed to be brought online in 2026 as well at Abilene Christian University. And I have actually talked to the guy in charge of that, and it's essentially a research reactor, but still a nice milestone to realize that we may have 2 molten salt reactors online in the US in 2026. Now, the Kairos plan is to end up with a 140 megawatt electric commercial power plant by the early 2030s. So at that point, they would actually be selling them to customers for use in power production. Another great thing about molten salt reactors, because you're running them at such a higher temperature, and instead of running them at like 300 C, you're running them at 650 C. You're getting better efficiency. So your typical nuclear power plant might have an efficiency of 33%, meaning that 2/3 of the heat is lost as waste heat. In this case, you're getting close to about half of the energy being useful. So you're really increasing your efficiency by close to 50% by running at that higher temperature. You're refueling online. You don't have to shut it down for a month to refuel it, which is great. And it has the auto-safe shutdown and passive cooling like the original MSRE. And even this reactor, even though it's using uranium, it can achieve a burnup of 19%. So yes, you still have a lot of unused fuel, but this is at least 5 times better than your typical nuclear reactor in terms of burnup. And this is just a quick diagram of the reactor, and essentially your pebbles of fuel are moving around in there, so they're not stationary like in a standard reactor. Another interesting reactor that I think is worth mentioning, even though it's not technically a molten salt reactor, it does use molten salt in some way. And that's the TerraPower Hitachi GE Natrium reactor. So this is being built in Wyoming, in Kimmer, Wyoming. And so this is the Bill Gates project, basically. And it's a sodium fast reactor. So it's running on that fast spectrum, using sodium to move things around, sodium to cool things. But it's tied to a to thermal storage. So in some concentrated solar power plants, they essentially use a different kind of molten salt to store the heat in tanks. And what they're proposing to do with this reactor is do the same thing, so that you can store some heat for later. And for this reason, this reactor actually has the ability to ramp up about 50% above its average power production. So its average is supposed to be 345 megawatts. It can ramp up to 500 megawatts for as long as 5.5 hours. But again, it has the advantage of running at atmospheric pressure. You don't need a massive containment building. They want to bring this online by 28, but there is a little bit of a shortage in HALEU supply right now, so they're saying possibly 2030. And this is a molten salt reactor, there's also molten chloride reactors. And so this is a chloride salt, but it runs basically the same way as the FLIBE reactor. This is being built at Idaho National Lab. And the goal of some of the molten chloride reactors at Idaho are to burn up the existing nuclear waste. So you can actually take that, remember I said 95, it's got 95% or better unused fuel in that waste, and you can actually reintroduce that fuel into this type of reactor and burn it up. So one of the guys in charge of that particular project, I heard him say in a presentation that, you know, he's not worried about using thorium yet until he uses up all the available spent fuel. And so this is just a very simplified thorium fuel cycle chart, but what it's basically showing you is that if you have your molten salt reactor going, you started off with uranium-235, but you surround it with thorium-232. That gets converted into U-233. You send it off for a while to, you know, let it go through that several week process, and then you reintroduce it to the reactor to burn as U-233 fuel. So you really can keep things going for a long time there. Now, one thing I'm not really showing you on this chart is the external salt processing over on the right there can be a pretty extensive chemical processing system on its own, but you may want, you're probably going to want that because you can pull things out of the salt that are very useful on the market. So, for example, actinium-225 is one of the elements that comes out of the thorium decay chain, and it is a very, very useful element in terms of cancer treatment. And there's just not enough of it available today. Another great thing about molten salt reactors, especially fueled with thorium, is so if you operate a light water reactor for 200 years, it's going to use 38,000 tons of mined uranium over that 200 years. But a thorium molten salt reactor over that same time frame would only use 600 tons of uranium and thorium. And then in terms of spent fuel, this is really great because a molten salt reactor, a thorium molten salt reactor, or even a uranium one, burns up 95, because it's liquid and you're able to move it around, it burns up 95 to 99% of the fuel versus the 1 to 5% for conventional light water reactors. So that means you end up with something like 4% of the waste as well. A light water reactor needs the long-term spent fuel to be in storage for like 10,000 to 1,000,000 years, whereas with the waste products of the molten salt reactor, 83% of the fission products, and I think this is specific to the thorium cycle, but 83% of the fission products are stable after 10 years and can be sold for industry and medicine purposes. And the remaining waste only needs storage for about 300 years. Compare that to 10,000 to 1,000,000. So what are some advantages of the thorium cycle? Low pressure coolant, fuel flow. We don't have that steam explosion issue. It's able to be used on that thermal spectrum I mentioned, the low absorption cross section. You can run it at a high temperature, and you need to with the molten salt, so it's much more efficient. You get much more power out of it. You can remove the waste, or actually it's not waste, but spent fuel products, fission products, in real time through those chemical processing techniques. You don't have to wait and do it later in some long, expensive process. You can remove xenon-135 essentially in real time. Now, why is that important? Well, a nuclear reactor produces xenon-135, and xenon-135 eats neutrons. It really likes neutrons. And if you get too much of it built up in your system, it'll start affecting your reactor power. And you want to be able to remove this stuff, or at least keep the amount of it manageable in your reactor. Well, in a molten salt reactor, xenon-135 is a gas, so it's just going to boil to the top of the molten salt, and then you have the opportunity to remove it. I already mentioned you have far less spent fuel. One thing that I didn't mention is that thorium-232, which you can convert to uranium-233, is about 400 times more abundant in the Earth's crust than uranium-235. So that means if you start using this for a source of fuel, you suddenly have the ability to, think about, we're talking hundreds, maybe thousands of years of power there. I mentioned the medical isotope production of the actinium-225. My dad is a walking miracle, despite the fact that he's never been treated with that. But he was diagnosed with prostate cancer when he was 64 and basically told he had months to live. Well, he's now survived it 4 times and he's 87. So I consider that a miracle. But if there was enough actinium-225 around to treat him, see, there's only enough of that produced today to treat maybe a few hundred people a year and in the world. And people they have treated, like, for example, with prostate cancer, were like basically cancer free in a matter of 3 or 4 months. Because this it has a half-life of like 10 days, and it can be essentially it attacks the specific cells it needs to attack in the body. And then you can also produce spacecraft fuel with this cycle, and we're getting rather short on plutonium-238. Now, this is different from plutonium-239, but it's used as a fuel in many unmanned spacecraft. Also, it would help with rare earth mineral production. Today, rare earth minerals are used in everything from wind turbines to electric cars to all kinds of the electronics we use. But often what you find in that, as you're mining the rare earth minerals, you find thorium. And right now it's just kind of a waste product. They don't know what to do with it. Well, we can use it. And of course, this is a fossil-free fuel source. Now there's always disadvantages and there's always challenges to developing a new technology. And that is happening today. And as I said, there's literally several hundred people around the world working on aspects of this. But I would say that of all the thorium challenge cycle challenges I've seen, I don't see anything that's really a showstopper. You might have already thought about when I mentioned that the molten salt doesn't become a gas until it's heated to like 1400 plus C. Why couldn't you make the molten salt reactor even hotter than 600 or 700 C? Well, the reason they typically don't is because you end up having, you have to contain this molten salt in your reactor, and you've got substances that have to be in constant contact with that molten salt. So you have corrosion issues. In theory, if you could keep all the oxygen and the water out of the molten salt, you keep it free of those things, you probably wouldn't have that much corrosion. But that is difficult to do all the time. But that's one of the reasons they keep the temperature at 700 C or less, because the corrosion issues are much lower if you do that. Lithium-7 is needed for liquid fluoride thorium reactors, and this minimizes tritium production. Now, tritium is something that is produced fairly abundantly in molten salt reactors. It's produced in all reactors, but it's a little bit more of a problem in molten salt reactors. So you have to think of a way how you're going to remove that. But you also need more lithium available for the reactors. And so both China and Kairos Power are developing industrial scale supply chains. So this is another thing. When you have a new technology, you have to develop supply chains for the parts and all the things you need that go with that, including even the salt. I mentioned before the beryllium toxicity issue. So if you're dealing with something like FLiBe, you have to deal with that. And people are working on getting more data on FLiBe's heat transfer properties. Now, this is an even worse problem when you're dealing with fusion power development. FLiBe stored at room temperature needs a chemical agent to prevent fluorine production. And there's more data needed on the purification requirements of the FLIBE. And chrome is needed in the structural alloy this has to do with the corrosion issues, but it is manageable if you keep the reactor under 700 C. I mentioned already that fission gases such as xenon and krypton can be purged with helium gas within 50 seconds of their production. So that part is great. Other noble gases that are produced can be purged within a few hours. I mentioned that today we use, and for many, many years for power production, we've used steam turbines. There is another way of converting the power that may be even better, and people are experimenting today with supercritical CO2. Supercritical CO2 is this is like being kind of like in a gas and liquid state, both. So if you raise the pressure enough and the temperature to the right point, you can get supercritical CO2. And here's what's really great about it. So if you see the chart here, what we use today is steam generators, and you see the steam is only really all that useful up to about 400 C. With the CO2, you can take it up to beyond where the 700 C that you typically use a molten salt reactor at. So supercritical CO2 may be a much better way of producing power and will even add more to the efficiency production. Now, I did mention that it runs under 85 times atmospheric pressure. So you might ask the question, well, does that get back into the problem we had with the water reactors running water under high pressure? Well, the answer to that is no, because so you see that guy standing there, he's standing next to a big steam turbine. Notice how huge the thing is. The size of a couple of buses, and that's typical for steam turbines. But I've also seen pictures of, and I didn't put it on here simply because it was copyrighted, but you can look up on the internet and find a picture of a guy holding the equivalent CO2, supercritical CO2 turbine, and it's like he can hold it in his hands. I mean, it's like just several feet long, so it's like 10 times smaller. So because it's that much smaller, running it under pressure is really not that big of an issue as far as an explosion or something. So I'll just finish off here by saying when I went to the Molten Salt Reactor Conference a few weeks ago, I was very pleased to see all the work that's going on. So as I said, private companies are actually building designing the reactors, but the national labs around the U.S. are doing a lot of the research that's needed to go into making this a reality. So, for example, Argonne National Lab is researching the salt circulation and instruments that you can use in those salts and use those salts. Idaho National Lab is doing salt testing, building a salt library. They're working on fuel cycle development and the waste burnup I mentioned. Pacific Northwest National Lab is working on advanced fuel cycles, off-gassing like the xenon and the krypton, and creating a market for, because there's people that want to buy these noble gases for other purposes that come out of these processes. They're working on removing water from the salt, making sure it's water-free, and doing radiation material stability testing, materials that will need to be in contact with radioactive salt. ORNL in Oak Ridge National Lab is working on licensing. So, the Nuclear Regulatory Commission is having to change the way it licenses reactors because all of their regulatory processing is based on light water reactors, and these are not light water reactors. ORNL is working on uncertainty quantification. They're working on the corrosion and materials issues. They're working on salt chemistry and oxygen removal. I know one guy was saying at the MSR conference that, yeah, if you keep the if you keep the oxygen out of the salt and you keep your salt clean, it works a lot better and you get a lot less corrosion. And then finally, Sandia National Lab, they're working on reactor safety and security, on fuel storage and transportation, and how do you dispose of molten salt. And then these are some of the, I already mentioned Kairos Power and TerraPower, but there are many other companies, and these all presented at the conference recently. Copenhagen Atomics, they are actually working on a large scale molten salt thorium cycle reactor, full-blown thorium cycle. They're hoping to set up a test reactor in 26 or 27 in Switzerland, although they're based out of Denmark. And then France has something called the Le Fleur commercial reactor they hope to produce by the 2030s. If you didn't know it, France is really big on nuclear power. France has really done well with nuclear power, with the nuclear power production for decades, and I'm glad to see them a part of this. Thorcon is another company. They're doing a thermal-based spectrum molten salt reactor in a specially designed can. In other words, you can transport it on a ship, and they actually have they're going to use mostly uranium, but some thorium. And but they have a contract with Indonesia to mass produce these reactors there. So I'm thinking probably 2030s for them as well. Most all of these are looking to have production reactors by the 2030s. The Willinga Innovation Foundation, they're working on a 500 megawatt molten salt reactor, working on a fast spectrum and chloride salts. Molten Flex, that's a British company, I believe. They're having some funding problems, but they are working on a 60 megawatt thermal graphite reactor, but it's all passive, so there's no active safety systems you have to worry about. The NAAAREA, they're working on small modular reactor with plutonium, and they expect to have a test reactor by 2031. They're kind of unusual because most people don't want to work with plutonium. Seaboard Technology, many of these are based out of Europe. Thermal molten salt reactor, graphite, 2% uranium. They're not using FLIBE. They're using what they call FUNAC, which basically uses fluoride, potassium, sodium. So they have a lower radioactivity issue with it, but they're expecting to have a test reactor by the early 2030s. And then finally, Stellaria, 200 megawatt light water plutonium or uranium plus thorium reactor in molten salt, a research reactor by 2027. So just to summarize it, no matter what your view is on climate or energy sources, we've got to work with the laws of physics we have. And that's where I think that energy return on investment really points to nuclear as being very important. Nuclear power provides at least 6 orders of magnitude more concentrated energy than fossil fuels. And that would be even greater if you compare it to solar and wind, which are very diffuse forms of energy. Moving to all renewable without nuclear just really doesn't add up economically or practically. Advanced nuclear solutions greatly reduce the already safety issues that exist with power plants in the nuclear power industry. And regardless of the magnitude of anthropogenic or natural climate change, advanced nuclear just really makes sense. And we were talking, I was talking, when we were getting set up, I mentioned I had driven through your area just a couple months ago. And so this is one of the pictures I took while I was out in California. And it's was a pretty sharp contrast for me since I'm used to paying about $251 right now. So, but anyway, I thank you for your time. And if anybody has any questions, I'll be happy to see what I can do.
Thank you very much, Kevin. That was a wonderful discussion and very thorough. I feel like I understand things a lot better. Can you comment on where in the world we find thorium? Are there certain countries that have an abundance and others that don't?
I know India is, we have thorium here in the US. Just it's fairly abundant in many parts of the world, but it often is associated with rare earths. So if you're mining rare earths, you're probably going to have thorium there. But there's already so much of it essentially laying around that I don't really think you'd have to mine it for a while because because of these other industries that exist where it's been mined as a byproduct they don't really need. There's plenty of it available. And so I really don't even know if we'd need to mine it for a while.
Interesting. Yes, Doug, did you have on Zoom? Did you have a question? You can unmute.
I did indeed. Uh, can you hear me?
Yes.
Are you able to hear me?
Yes, we can hear
Okay.
you, Doug. Go ahead.
So I had two questions. Okay. I had two questions, if I may. My understanding, and I want to know if this is correct, is that one of the major reasons for the low adoption, shall we say, of nuclear is that environmental movement successfully basically regulated the industry into oblivion. Would like to know if you share that view and maybe could comment on it. That's question one. The question two is that my understanding again of the history was that we have uranium reactors basically because of the need to also support military applications, and thorium was basically not pursued because it has minimal military application. I was wondering if you agree with that or if that's a mistaken view.
Those are great. Those are great questions. And I think I'll start with the second one first. I think, yes, that issue does tie into military applications. And I think that's part of the reason it wasn't pursued in the 70s, because there was an interest in plutonium production. But today things are different. Today we're wanting to avoid proliferation of those types of materials. So if you can produce the energy in a way that is less conducive to proliferation, then that's a plus now. So uranium-233, like any uranium, could be, in theory, turned into a bomb. But the advantage of it is that, first of all, you're not going to produce much plutonium from it at all. So that's good. The second part is uranium-233 has some radioactive properties that if you enrich it, like you would need to do in bomb making, you're essentially going to kill yourself unless you're not really, really careful, because it has some radioactive, it gets much more radioactive is what I'm saying as you try to. So if you just enrich it a little bit for power production, you're probably fine. But if you start enriching it like they do with other forms of uranium or plutonium, it's much harder to use for that purpose. So while technically not impossible, I've never heard of anybody trying to use it for that. It's just much easier to work with other fissile materials. As far as the politics of nuclear power in general, the first question, there could be, I think that factors, I think the environmental issues factor into it. I think a lot of it also factors into these well-publicized nuclear accidents. And people just have an oversized fear of nuclear and radiation because I think that just there's not enough understanding about it. I'll give you one great example. When Fukushima happened in 2011, I've been running part of my job. I've been running dispersion models like for potential radioactive accidents. So for years, and I've so I had a pretty good idea of, if you model a release of some radioactive material, how bad is it going to be? Well, in Knoxville, Tennessee, close to where I live, they had a headline after Fukushima that said, Fukushima plume reaches East Tennessee. And if you check into the data, it's like half of the background radiation. I mean, I knew from my modeling experience that if you were more than, say, 10 to 20 miles from Fukushima, you really probably didn't have anything to worry about, let alone all the way on the other side of the world. You know, now with Chernobyl, it was a little bit worse than that. It still wouldn't have been on the other side of the world, but there were some pretty significant areas, let's say within 20, 30 miles that might have been concerned with Chernobyl. But the good news is I think people are starting to see, even on not just the right or the left, but I have actually seen some support for these advanced reactors from both sides of the political spectrum. And that's something that I haven't seen with most other energy sources, especially if it's in the context of climate change. So I am encouraged by that. I mean, I'm really seeing people on different sides of the political spectrum support this. Now, I do think it's still probably a little more supported on the right than the left, but there is support, and it's growing. So I am encouraged by that.
So just a quick follow-up to that question. It seems to me that the nuclear industry in this country is regulated way beyond almost any other industry you can imagine. That it seems that, things like zero threshold exposure limits for uh, for people, for instance, that are required. These are, even chemical industry doesn't have to deal with that. It just seems to me that it's been regulated to an extreme degree, partly, I suppose, because of what you just said. There's this fear of the N word in almost anything. Is that how you see
I
it?
would, I would basically agree with that. I think there is some streamlining of regulation that needs to happen, and I do see some positive signs that the NRC is trying to work with this new technology, but maybe we need to go a little further with it. Frankly, there are some of these companies I mentioned that have chosen to work overseas for that very reason. So, for example, Thorcon was able to work much more readily with Indonesia than they were able to do something in the US. So that is something we need to look at. I mean, I'm familiar with some of the nuclear programs in other countries, and like India, for example, has a very streamlined process. They have a lot of can-do Canadian reactors, but they have a very streamlined process the way they're building them. And I think we need to start doing that here again. One of the reasons the power plants that were just built in Georgia that just came online, they went way over budget. But part of the reason for that is because it's been so long since we've really built a nuclear plant in the U.S. that a lot of the know-how and the expertise just wasn't there anymore, and it was, everybody knows that when you build the first of a kind of something, and that's what we're facing with some of these molten salt reactors, it's much more expensive at the beginning. And so it's almost like we went part of the way back to that with some of these new, uh, what we might call conventional reactors, because it's been so long since we built one. The first, I think I'm talking about the Vogel plants in Georgia, but the first nuclear reactor in the 21st century to be brought online was in about 2016 or 17, right down the road from me here, the Watts Bar Unit 2, which had actually been started 20 or 30 years ago and then kind of mothballed for a while, and then they finally got it running. So we're just now getting to a point where we're starting to bring online reactors again in the U.S. I think that will get better, but we do need to streamline a lot of a lot of the whole process. It just takes way too long.
Thank you.
Hi, my name is Brian. I work in the buffering side of the power grid. I work in fluidized beds, sands, energy storage, thermal energy storage, for which I have a patent. I know the Canadians are working on this idea also. Do you guys need something like that where you're located, doing research?
Well, I'm not really directly in contact with people doing that, but I wouldn't be surprised if there were people interested. I know there are a number of nuclear companies here that are setting up shop in the Oak Ridge area, and I would think that at least some of them would have an interest in that. Um, the only one of those companies that I know anybody personally in is Kairos, um, because they're building one of their reactors here in Oak Ridge.
Okay. I also have designed a thermal hydraulic pump. It's kind of like a Stirling, but different. But basically, you can take heat and turn it directly into hydraulic pressure.
I
And
would I would strongly suggest that next year, and I wish I could give you some names. I really don't know, but I think that if you came to the molten salt reactor conference and talked to some of those people, I think there might be some people interested there. Um, they just had it, so it'll probably be, next October or November before it comes around again. But
okay, thank you.
Any other questions for Kevin, either those on Zoom or here in the room? I might make a comment. I know that now with AI being very extensive and growing, it's extremely power dependent. And so I suspect with a number of companies instigating that I've heard that some of them even wanting to build their own power plants. Are you familiar with that? And what do you see as the future, given the demand of energy for AI?
well, it's only increasing the realization that nuclear is needed. You probably heard there was just a contract set up for that very purpose to restart some of the 3 Mile Island reactor. So I think there's three reactors there, and it was one that melted down in 1979, and the other two continued to run until about 5 years ago when they were shut down. And those are now going to be restarted for the AI purpose. Um, but I'll just throw in here 3 Mile Island is that was the worst accident that we've had in the US, and it was basically a nothing burger as far as uh, people safety. Now it was expensive for the company, but you get about 300 millirems of radiation in an average place in the US just living every year. Um, 3 Mile Island added 1.5 millirem to the dose around its area, its little local area there. So not even more than 0.5% of background radiation. So it was really insignificant.
Yeah, but what do you see as the major obstacles, political or otherwise, to really moving forward with this technology?
I think, well, up until a few weeks ago, I would have said I'd like to see more of a government effort getting behind it, kind of like they did with the moon mission in the 60s. Because anytime you do something like this, a new type of technology in a way, even though it was done in the past and then sort of shut down, um, there's just a lot of new things to learn, and it can be a 20-25 year process sometimes. So, we've got to do everything we can to be proactive to speed it up. But I think, it is what it is. And that's unfortunately, the interest in it was gone for about 30 or 40 years, and then thankfully it's back. But we're still probably looking at another decade before we start to get molten salt reactors as part of our power grid.
I have a question for you.
Sure.
It seems like before this lecture, I've kind of viewed nuclear power as a monolithic type of endeavor. But now my eyes are open to the fact that there's just an explosion of a wide array of technologies. And when did that start? I mean, what's the history on that?
Well, as I think I alluded to it started in the 60s. I mean, they built the molten salt reactor experiment in a year in the mid 60s without all the regulation. But it's only been, the light water reactors just really took over everything. And that was the standard until, let's say I'd say the beginning of the 2000s, things started to change, but it didn't really start to get any speed until the 2010s. And now, I was very encouraged at the MSR conference a few weeks ago that there were actually 400 people actively working on aspects of this technology in at least 6 national labs uh, and at least a dozen private companies. That's actually more than I thought was going on, which is good. But I think we need that and more. Um, there's just such a need for more power, and if the goal is to do it fossil free, then I don't see another way to get anywhere close to that without you're just not going to be able to put up enough solar panels and windmills to really solve the problem. And by the way, I didn't mention it, but I am involved in a small project, or in a small way in a project right now in wind turbines. And wind turbines are basically worth the investment on land, but there is a desire to put them on the ocean where there's more wind and in coastal areas. But the problem is they're about 4 times more expensive. And so the big challenge is, how do you get the cost down? And right now, that's the problem. They're really just not, they don't meet that EROI requirement, at least when you're dealing with offshore wind.
Any other questions? The question is, can we get your contact information?
Oh, sure. I can, I could, I don't, well, you want me to email it to you,
Or we have it. It's okay to give it out. I mean, we
Okay.
have an email if that's all right to use.
That's fine.
Is that okay? Thank you. Just make one comment, and that is that on this earth, one of the providential things is we have an abundance of uranium and thorium, more than we would have expected in our planetary system. And it just, I think, as we had mentioned earlier, just that if God is providential in giving us an option to have an energy source that is good for the world, good for us, and maintains enough energy that people can have the services and survive in advanced civilization. So
I totally agree with that.
remarkable.
I think it's there for a reason.
I have a question about, you mentioned that new systems can burn up some of the old fuel that's just wasted, the 95% of the uranium-235 and so forth that's wasted. When they're putting all the so-called waste in these containers and burying them under hills and stuff, does that ruin it from the possibility of recycling it and reusing it?
Most of the time, well, I think, for example, there's a location in southern New Mexico where, you know, it's accessible. It's not, I mean, it's not like they cover it up like a casket or something. Even it's more like, you know, caves with storage sections, and I mean, it's not a cave either, but it's, you know, it's where you can get to it. So I think that's I don't think that's going to be an issue.
Thank you.
Other questions? Any other questions from anyone on Zoom? Well, then Kevin, I'd really thank you so much for this time tonight. You know, wonderful talk and very educational, and really gets us thinking in different directions. So thank you very much. And we know you are Tennessee, so you're 2 hours ahead of us. So we want to respect your time and thank you for taking the extra time to be here with us this evening.
Oh, you're welcome. I appreciate it.
Okay, well, thank you so much. And we will conclude our Zoom portion. Again, thank you again for being here, and thank you for all of you who are on Zoom. And we will, next month, we will not be here because it's right before Christmas. So we will take the month off. And then January, we'll be back. We have a really interesting presentation on amazing DNA. So we're going to get back into biology a little bit in January. So we're looking forward to that. And thank you all for coming. And we have the room till 9, so feel free to hang around. And thank you, Julie, for bringing snacks.
Yeah.